Where are you right now? Scrolling through your phone at 2 a.m? Procrastinating on something important? Maybe you're supposed to be studying for finals, but instead you're here, deep in the rabbit hole of YouTube, looking for something, anything, to fill that restless void in your brain. Well, bored people, you found the right place. This is Muted History, where we tell the stories that textbooks forgot to make interesting. The chapters that got buried under layers of academic dust and sanitized timelines. Tonight, we're going back, way back, to a moment when Earth itself was having an existential crisis, when the planet looked up at the sky, saw a mountain of rock and ice screaming toward it at cosmic speeds, and basically said, well, this is going to hurt. This is the story of how everything died and then how everything began again. Not the sanitized version you learned in school, but the raw, chaotic, beautiful mess of what actually happened when our planet hit the reset button 66 million years ago. If you're here for quick answers and clean timelines, you're in the wrong place. But if you want to understand how a ball of molten hellscape somehow became the world that grows your morning coffee, stick around. This isn't just about dinosaurs dying. This is about what comes after the apocalypse. This is about how life doesn't just survive extinction, it gets creative with it. So dim your screen, get comfortable, and let me tell you about the most epic comeback story in planetary history. Because what happened after the asteroid hit wasn't just recovery, it was revolution. Picture this: Earth, 66 million years ago, the Cretaceous period. If you could somehow travel back and walk around, you'd think you'd landed on an alien planet. The air is thick, humid, almost tropical everywhere. There are no ice caps, no frozen poles, just endless warmth wrapping around a world that barely recognizes seasons. The oceans are shallow and vast, cutting continents into archipelagos of steaming islands. And everywhere, absolutely everywhere, there are dinosaurs. Not the Hollywood dinosaurs you're thinking of. Real ones, bizarre ones, duck-billed hadrosaurs, the size of school buses, honking at each other across misty river deltas. Massive sauropods, long-necked giants that make modern elephants look like house cats, methodically stripping entire forests bare. In the oceans, mosasaurs, marine reptiles longer than sperm whales, patrolling warm seas filled with ammonites, spiralling through the water like living nautilus shells. And then there's Tyrannosaurus rex, but not the lumbering movie monster, the real thing. A 40-foot-long predator with forward-facing eyes, binocular vision, and a bite force that could crush a car. T-Rex wasn't just big, it was smart. Recent discoveries suggest these animals lived in family groups, possibly even hunted in coordinated packs. They were the apex predators of a world that had never known anything like human intelligence, but was teeming with a kind of ancient reptilian genius. This wasn't a world waiting to die. This was a world at its peak. Biodiversity was off the charts. Ecosystems were stable, complex, thriving. If you were an alien anthropologist studying Earth 66 million years ago, you might conclude that reptiles were the planet's chosen inheritors, that this was how life was supposed to work. Mammals existed, sure, but they were tiny, nocturnal, basically living in the cracks of a dinosaur-dominated world. Most were no bigger than rats, scurrying through underbrush, trying not to get stepped on. The largest mammal of the late Cretaceous was about the size of a badger. That's it. While 30-ton triceratops were having territorial disputes and pterosaurs with 35-foot wingspans were ruling the skies, our ancestors were hiding in burrows, eating insects, and trying to stay invisible. If you had to bet on which group would inherit the Earth, mammals wouldn't even make the list. But here's the thing about extinction events. They don't care about your resume. They don't care how well adapted you are, how long your lineage has ruled, how perfectly you fit your niche. Sometimes the universe just rolls the dice and everything changes in an instant. The Chicxulub impactor, as scientists now call it, wasn't just a rock, it was a mountain, 6 miles across, travelling at 45,000 miles per hour. To put that in perspective, imagine something the size of Mount Everest moving 60 times faster than a bullet. When it hit the Yucatan Peninsula, it released energy equivalent to 10 billion atomic bombs going off simultaneously. The explosion created a crater 93 miles wide and 12 miles deep, instantly vaporizing everything within a 600-mile radius, but that was just the beginning. The impact threw massive chunks of Earth's crust into space, creating a brief, artificial ring system around our planet. As this debris fell back down, it superheated the atmosphere, turning the sky into a broiler. The surface temperature spiked to over 300 degrees Fahrenheit. Forests around the globe simply burst into flames. If you were a dinosaur anywhere on Earth that day, you were about to have a very bad time. The immediate kill zone was horrific, but it was nothing compared to what came next. All that vaporized rock, all that debris, all those particles of impact glass, they didn't just disappear, they formed a global cloud that blocked out the sun. Not for days or weeks, but for months, maybe years, the planet went dark. Photosynthesis stopped. Just like that, the entire food web collapsed from the bottom up. Plants died, herbivores starved, carnivores followed. The oceans turned acidic from all the atmospheric chemistry chaos. Marine ecosystems, which had been stable for millions of years, simply dissolved. It wasn't just an extinction event, it was a planetary reboot. And here's where the story gets interesting, because while 75% of all species on Earth went extinct, some things survived. Not the big things, not the impressive things, not the things that looked destined to rule the world. The survivors were small, adaptable, and really, really good at hiding. Mammals, it turns out, had been practicing for this moment their entire evolutionary history. Living small, staying flexible, being able to eat basically anything, maintaining stable body temperatures, caring for their young in ways that reptiles couldn't match. All those traits that had kept them in the shadows suddenly became superpowers in a world where being big and specialised meant death. But mammals weren't the only survivors. Birds, which are technically dinosaurs themselves, made it through. So did crocodiles, turtles, some lizards, and snakes. Sharks kept doing shark things in the oceans. Insects, those indestructible little machines, barely noticed the apocalypse. And in the plant kingdom, seeds were literal time capsules, waiting in the soil for the light to return. The question is, what happened next? How do you rebuild a world from the ashes of the previous one? How do you go from a planet of hiding, rat-sized mammals, to a planet where mammals grow as large as blue whales and develop brains complex enough to figure out what killed the dinosaurs in the first place? The answer is both simpler and more incredible than you might think. Nature abhors a vacuum, especially an ecological one. When the dust settled and the sun finally broke through the debris cloud, Earth was essentially a blank canvas. All those ecological niches that had been occupied by dinosaurs for 165 million years were suddenly open for business, and mammals, despite their humble beginnings, were about to go on the most spectacular evolutionary shopping spree in the history of life on Earth. But this wasn't a gentle transition. This was chaos. Beautiful, creative, explosive chaos. In the geological blink of an eye, mammals began experimenting with body sizes, diets, locomotion, and lifestyles that would have been impossible in a dinosaur-dominated world. Some grew enormous, others stayed small but got incredibly smart. Some took to the trees, others to the water. Still others learned to fly. Within just 10 million years after the extinction, mammals had produced giants that dwarfed anything alive today. Within 20 million years, they had carved out ecological roles that dinosaurs never even attempted. And within 60 million years, they had produced something that the planet had never seen before. A species capable of looking back through deep time and understanding its own origins. This is the story of that transformation. Not just what survived the asteroid, but how the survivors became something entirely new. How tiny, scurrying creatures became the dominant life forms on a planet that had forgotten what dominance even meant. How the meek didn't just inherit the Earth, they redesigned it from the ground up. And the wildest part, we're still living in the aftermath of that ancient catastrophe. Every mammal you've ever seen, from the smallest shrew to the largest whale, from your pet dog to the human reading these words, exists because a mountain-sized rock happened to crash into the Yucatan Peninsula at exactly the right angle, at exactly the right speed, at exactly the right moment in Earth's history. If that asteroid had been slightly smaller, slightly larger, if it had hit the ocean instead of land, if it had arrived a few million years earlier or later, the world would be completely different. Maybe dinosaurs would still rule. Maybe mammals would still be hiding in the shadows. Maybe intelligence, as we know it, would never have evolved at all. But it didn't happen differently. It happened exactly the way it happened. And the result is the world we live in today, a world where the descendants of small frightened creatures have become the planet's dominant species, capable of art and music and science and love, capable of looking up at the night sky and wondering where we came from. That's what makes this story so incredible. It's not just natural history, it's our history. The asteroid that killed the dinosaurs didn't just end one chapter of life on Earth, it began another, our chapter, and understanding how that transition happened, how life rebuilds itself after total catastrophe, how evolution fills empty spaces with unimaginable creativity. That's not just science, that's hope. Because if life can come back from a literal apocalypse, if it can take the worst thing that ever happened to the planet and turn it into an opportunity for something entirely new, then maybe there's no catastrophe that can't be overcome. Maybe destruction and creation are just two sides of the same cosmic coin. Maybe the end of one world is always the beginning of another. So that's what we're here to explore, bored people. Not just what died when the asteroid hit, but what was born from those ashes. Not just how the dinosaurs ended, but how everything else began. This is the story of Earth's greatest comeback, told in the only way it deserves to be told, as the epic, chaotic, beautiful mess that it actually was. Stay with me, because this is just the beginning. We're about to dive into the Paleocene, the age that came after the apocalypse, when mammals first opened their eyes in a world without dinosaurs and realised they were no longer prey. They were pioneers in a broken world, and they were about to build something incredible from the ruins. The first thing you need to understand about the Paleocene epoch is that it was basically the world's most chaotic garage sale. Imagine walking into a house after a hurricane has blown through it, except the house is an entire planet, and the hurricane was a 6-mile-wide asteroid. Travelling at cosmic speeds, everything is broken, scattered upside down. But here's the weird part. Some stuff survived, and now all that stuff has to figure out how to live together in ways that make absolutely no sense. Welcome to Earth, 65 million years ago. The dust has settled, literally. The global firestorm is over. The acid rain has stopped falling. The sun is finally peeking through the debris cloud that's been choking the atmosphere for months, maybe years. And in this strange, wounded world, something unprecedented is happening. The survivors are emerging from their hiding places, blinking in the unfamiliar light, and slowly realising that all the rules have changed. Picture the scene, bored people. You're a small furry mammal about the size of a squirrel. For your entire evolutionary history, your species has lived in terror. Every day was about staying hidden, staying quiet, staying alive. Your ancestors spent 100 million years perfecting the art of being invisible, scurrying through underbrush in the dead of night, eating whatever scraps the giant reptiles left behind. You were prey. That was your job description. That was your entire identity. But now you poke your head out of your burrow, and something's different. The ground isn't shaking with the footsteps of 30-ton herbivores. The sky isn't filled with the shadows of pterosaurs. The air doesn't carry the scent of massive predators marking their territory. For the first time in your species' memory, the world is quiet, not peaceful. There's nothing peaceful about a post-apocalyptic landscape, but quiet in a way that feels almost supernatural. You venture further from your hiding place, then further still. And slowly, it dawns on you, the giants are gone. All of them. The tyrannosaurs that could have swallowed you whole without noticing. The massive sauropods that treated entire forests like salad bars. The armoured ankylosaurs that turned walking into a geological event. They're gone and they're not coming back. This is the moment when mammalian evolution shifted from defence to offence, from survival to expansion, from hiding in the cracks of someone else's world to realising that the world itself was suddenly up for grabs. But here's where the story gets really weird, because the early Paleocene wasn't some mammalian paradise where our ancestors immediately started growing into giants and taking over. No, the first phase of the post-dinosaur world was actually dominated by something much stranger: crocodiles. Yeah, you heard that right. While mammals were still figuring out that they didn't have to whisper anymore, crocodiles were having their moment. These weren't the semi-aquatic ambush predators we know today either. We're talking about fully terrestrial crocodiles, some of them massive, some of them fast, some of them with legs built for running rather than crawling. There was Dinosuchus, a land crocodile the size of a city bus with teeth like railroad spikes. There was Pristichampsus, a crocodile that ran on its hind legs like a dinosaur, but with the predatory instincts of something that had survived the apocalypse by being tougher than everything else. For about 10 million years after the extinction, these crocodilians were the apex predators of the New World. They filled the ecological roles that tyrannosaurs and other large dinosaur predators had left empty. And mammals? Mammals were still playing it safe, still staying small, still acting like prey animals, even though their predators were gone. This is one of the most fascinating aspects of evolutionary psychology that we can observe in the fossil record. Even when the threat disappears, the trauma response persists. Mammals had been programmed by 100 million years of evolution to stay small, stay hidden, stay scared. You don't just flip a switch and turn off instincts that have kept your lineage alive since the Jurassic period. It takes time for evolution to realise that the rules have changed. But while mammals were being cautious, something else was happening that would ultimately matter more than size or strength or teeth. They were diversifying, not in obvious ways, not in dramatic ways, but in subtle experimental ways that would eventually reshape the entire planet. See, when you're small and adaptable, you can afford to try things. You can explore different diets, different habitats, different ways of moving through the world. And that's exactly what early Paleocene mammals started doing. Some species began specialising in eating seeds and fruits from the new plant communities that were emerging in the post-impact world. Others focused on insects, which were abundant and diverse. Still others became more carnivorous, hunting smaller vertebrates. This dietary diversification was crucial because it set up the foundational food webs that would support everything that came later. You can't have giant predatory mammals until you have medium-sized herbivorous mammals. You can't have those until you have small omnivorous mammals efficiently converting plant matter and insects into mammalian biomass. The Paleocene mammals were laying the groundwork, building the ecological infrastructure that would eventually support a mammal-dominated world. And here's something that might blow your mind. They were already getting weird. Like, really weird. There was Taeniolabis, a beaver-sized mammal with massive grinding teeth that could crack nuts the size of coconuts. There was Patillodus, a squirrel-like creature that could glide between trees using skin flaps, basically inventing powered flight for mammals 60 million years before bats figured it out. There was Barolambda, a bear-sized omnivore with claws like garden spades, probably the first mammal that was genuinely too big for a crocodile to mess with. But the real innovation was happening at a level you couldn't see from the outside. Mammalian brains were changing, not dramatically, not obviously, but consistently. Each generation was dealing with more complex social situations, more varied food sources, more diverse environmental challenges. The selective pressure wasn't just don't get eaten anymore, it was figure out how to make the most of this new world. And mammals had some serious advantages in that department. Unlike reptiles, they could maintain stable body temperatures, which meant they could be active at night, in cold weather, in conditions that would shut down cold-blooded animals. They had more sophisticated parental care, which meant knowledge and behaviours could be passed from generation to generation more effectively. They had more flexible metabolisms, which meant they could exploit food sources that other animals couldn't access. Most importantly, they had social structures that were already more complex than anything reptiles had developed. Many early mammals lived in family groups, communicated with vocalizations, engaged in play behaviour, showed evidence of emotional bonding. These might seem like minor details, but they were actually revolutionary adaptations for a world where cooperation and information sharing were becoming more valuable than individual strength. Because here's the thing about post-apocalyptic worlds, they're unpredictable. The old stable ecosystems were gone. Climate was chaotic. Food sources appeared and disappeared. Migration routes changed. In an environment like that, the species that could adapt quickly, share information effectively, and work together to solve problems had enormous advantages over species that relied on size, strength, or specialized adaptations. Mammals had been accidentally preparing for this kind of world for millions of years. All those traits that had kept them small and hidden in the Mesozoic, flexibility, adaptability, social cooperation, parental investment, suddenly became the keys to success in the Cenozoic. But the really crazy part is what was happening to the planet itself during this time. The Paleocene wasn't just about animals recovering from the extinction. It was about the entire Earth system rebooting itself from the ground up. The impact had triggered massive climate changes that were still playing out decades after the dust settled. Ocean circulation patterns had been disrupted, which meant heat distribution around the planet was completely different from what it had been during the Cretaceous. Atmospheric chemistry was still recovering from all the vaporized rock and organic matter that had been thrown into the air, and the plant communities were going through their own revolutionary changes. See, when you kill off 75% of all plant species on the planet, you don't just get a smaller version of the same ecosystem, you get something entirely new. The plants that survived the extinction weren't necessarily the most common or the most successful plants from before. They were the ones that happened to have traits that helped them survive global firestorms, months of darkness, and dramatically altered soil chemistry. Many of the surviving plants were opportunistic species, things like ferns that could quickly colonize disturbed ground, or plants with seeds that could remain dormant for long periods and then germinate when conditions improved. These weren't the massive conifers and cycads that had dominated Mesozoic forests. These were scrappy, adaptable, fast-growing species that could take advantage of the ecological chaos. And as these plant communities established themselves, they created new opportunities for the animals that fed on them. Mammals that could efficiently process the new types of seeds, fruits, and leaves had access to resources that hadn't existed in the dinosaur world. This drove further diversification as different mammalian lineages specialized for different types of plant foods. But perhaps the most important change was happening in the oceans. Marine ecosystems had been devastated by the extinction, but they were recovering in ways that would fundamentally alter the planet's carbon cycle and climate system. New types of plankton were evolving, different patterns of ocean productivity were establishing themselves, and all of this was affecting atmospheric CO2 levels, which was affecting global temperature, which was affecting rainfall patterns, which was affecting terrestrial ecosystems. The Earth was becoming a different planet, not just biologically, but physically and chemically. And mammals were evolving alongside these changes, adapting to new climates, new plant communities, new opportunities and challenges that their Mesozoic ancestors could never have imagined. By the end of the Paleocene, about 10 million years after the extinction, the mammalian experiment was clearly working. Species diversity was exploding. Body sizes were starting to increase. Ecological roles were being filled that had never existed before. And most significantly, mammals were beginning to develop the kinds of complex behaviours and social structures that would eventually lead to intelligence, culture, and everything that makes mammalian societies so remarkably sophisticated. But we're still just at the beginning of this story, bored people. The Paleocene was just the warm-up act, the opening band before the main event, because what came next, in the epoch called the Eocene, was when mammals really started to get creative. When they began to experiment with body plans and lifestyles that would make the dinosaurs look conservative by comparison. We're talking about the epoch when mammals first tried out being giants, when they first experimented with living in the oceans, when they first developed the kind of complex social behaviours that would eventually evolve into human civilization. The Eocene was when mammals stopped playing it safe and started pushing the boundaries of what it meant to be a warm-blooded, live-bearing, milk-producing vertebrate. And trust me, they pushed those boundaries in ways that will absolutely blow your mind. So stay with me as we dive into the age when mammals went from being survivors to being innovators, when they transformed from creatures hiding in the shadows of giants to giants that would cast shadows of their own. The Eocene epoch, bored people, was when mammals basically looked at the rulebook of vertebrate life and said, you know what, let's throw this whole thing out and start over. We're talking about the period from 56 to 34 million years ago, when our ancestors went from playing it safe to conducting the most audacious biological experiments in Earth's history. This wasn't just evolution anymore, this was revolution. Picture the world 50 million years ago and try to wrap your head around this. It was hot, not summer in Arizona hot, not even Death Valley in August hot. We're talking about a planet where palm trees grew at the North Pole, where crocodiles sunbathed in the Arctic Ocean, where the global average temperature was about 80 degrees Fahrenheit compared to today's 60 degrees. The Eocene was Earth's tropical fever dream, and mammals were about to take full advantage of it. But here's what makes this period so mind-bending. Mammals weren't just adapting to this hothouse world, they were reshaping it. They were filling ecological niches that had never existed before, creating new ways of being alive that the dinosaurs, for all their success, had never even attempted, and they were doing it with a creativity that borders on the absurd. Let's start with the obvious question. How big can a mammal get? During the Mesozoic, the answer was about the size of a badger, and you better hope nobody notices you. But in the Eocene, mammals looked at that limitation and laughed. They didn't just get bigger, they got ridiculous. Meet Wintertherium, a creature that looked like someone had taken a rhinoceros, given it the brain of a walnut, and then decided it needed more horns. We're talking about an animal the size of a large elephant, with 6 bony protrusions sticking out of its skull like some kind of prehistoric punk rocker. These things had canine teeth, like sabers, tiny brains, and absolutely no sense of proportion. They were living proof that sometimes evolution just gets weird for the sake of being weird, but Wintertherium was just the opening act. The real star of the Eocene-size Olympics was a group of mammals called Brontotheres. And yes, before you ask, they were basically the mammalian answer to sauropod dinosaurs, except somehow even more over the top. Imagine a creature the size of a large elephant, but with the proportions of a rhinoceros and a head that looked like it was designed by someone who had only heard descriptions of mammals secondhand. The largest of these, Brontotherium, stood 8 feet tall at the shoulder and weighed as much as 3 cars. It had a skull over 3 feet long, topped with a massive Y-shaped horn that made it look like a biological battering ram. And here's the kicker. These animals were browsers. They used all that size and weaponry to eat leaves. Delicate, tender leaves that they probably could have reached just fine without turning themselves into living siege engines. But mammals weren't content to just get big. They wanted to get big in every possible direction. Some went tall, like the Brontotheres. Others went long, like Coryphodon, a hippo-like creature that was basically a mammalian barrel with legs, designed for a life of aggressive plant consumption. Still others went wide, like the early proboscideans, the ancestors of elephants, who were experimenting with the basic concept of, what if we made a nose that could pick things up? And then there were the ones that went completely off script. Mammals that looked at the basic mammalian body plan and decided it needed significant modifications. There was Gastornis, a flightless bird the size of a grizzly bear with a beak that could crack coconuts, stalking through Eocene forests like something out of a fever dream. Except here's the plot twist. Recent evidence suggests these terror birds were actually herbivores. They were using those massive bone-crushing beaks to crack nuts and seeds. Evolution's idea of a practical joke. But size was just the beginning of the Eocene mammalian weirdness. The real innovation was happening in terms of lifestyle, behaviour, and ecological roles. Mammals were experimenting with ways of being alive that no vertebrate had ever tried before. Take the early primates, for example. Our own ancestors were among the mammals getting creative during the Eocene, but they weren't getting bigger, they were getting smarter. Early primates like Darwinius, the famous Ida fossil, were developing forward-facing eyes, grasping hands, and the kind of complex social behaviours that would eventually lead to language, culture, and the ability to figure out what killed the dinosaurs. These early primates were living in dense tropical forests that covered much of the northern continents. They were developing the kind of three-dimensional thinking that comes from navigating complex arboreal environments. They had to judge distances between branches, remember the locations of fruit trees, navigate social hierarchies within their groups, and avoid the various predators that were also getting creative in the Eocene forests. And speaking of predators, this is where the Eocene gets really interesting, because mammals weren't just experimenting with being big herbivores. They were also figuring out new and terrifying ways to be carnivores. The creodonts were mammals that looked at the extinction of the dinosaurs and thought, you know what this world needs? More things with really, really big teeth. These weren't related to modern carnivores. They were their own evolutionary experiment in mammalian predation, and they got weird with it. There was Sarcastodon, a bear-like predator the size of a grizzly, but with the skull proportions of a hyena and teeth that belonged on something twice its size. This thing could crack bones like walnuts and probably hunted some of those massive herbivores we talked about earlier. Then there was Hyenodon, which despite its name wasn't related to hyenas at all, but was a long-bodied, short-legged predator that looked like someone had stretched a wolverine to the breaking point and given it the attitude to match. But the real stars of Eocene predation were the mesonychids. These were mammals that looked at the basic wolf body plan and decided it needed to be about 3 times larger and significantly more terrifying. Andrewsarchus, the largest known land mammal predator of all time, had a skull 3 feet long and jaws that could generate bite forces comparable to a large crocodile. This thing was essentially a mammalian tyrannosaur, prowling Eocene landscapes and reminding everyone that mammals could be just as scary as anything that had come before. But here's where the story takes a turn that nobody saw coming. Because some mammals in the Eocene looked at all this terrestrial experimentation and thought, this is cool and all, but what if we tried living in the water instead? This is when mammals made one of the most audacious evolutionary decisions in the history of life on Earth. They decided to go back to the ocean. Not to visit, not to hunt along the shoreline, but to fully commit to an aquatic lifestyle. To essentially reverse 300 million years of vertebrate evolution and return to the sea. The early whales of the Eocene were some of the most bizarre creatures that ever lived, because they were caught in the middle of this transition. They were mammals that still had 4 legs, but were trying to figure out how to swim. They had teeth like wolves, but were learning to hunt fish. They could walk on land, but were most comfortable in the water. Ambulocetus, the walking whale, was about the size of a large crocodile, but with the proportions of a stretched-out otter. It had massive hind limbs for swimming, but also functional forelimbs for walking on land. Its skull was elongated, like a crocodile's, but its teeth were distinctly mammalian. It was a creature caught between 2 worlds, and it was magnificent. But Ambulocetus was just the beginning. Over the course of the Eocene, whales went through one of the most rapid and dramatic evolutionary transformations ever documented. They lost their hind limbs, developed flippers, moved their nostrils to the tops of their heads, and completely restructured their inner ears for underwater hearing. Within 20 million years, they went from wolf-like land animals to fully aquatic leviathans, and they weren't the only mammals making the transition to aquatic life. Early sirenians, the ancestors of manatees and dugongs, were also experimenting with marine lifestyles. Early pinnipeds were figuring out how to be both terrestrial and aquatic. Mammals were basically trying out every possible way of interacting with water, from wading to swimming to diving to full-time oceanic living. But perhaps the most remarkable thing about the Eocene wasn't any single species or adaptation. It was the sheer diversity of experiments that mammals were conducting simultaneously. They were trying out new body sizes, new diets, new habitats, new social structures, new ways of moving through the world. It was like evolution had been given unlimited research funding and told to go crazy. In the forests, early horses about the size of house cats were learning to run on grasslands that didn't exist yet. Early elephants with short trunks and multiple tusks were figuring out how to be giants without falling over. Early bats were perfecting powered flight and echolocation, becoming the first mammals to truly conquer the skies. Early rodents were developing the kind of reproductive strategies that would eventually make them the most successful mammalian group on the planet. And through it all, the planet itself was changing. The Eocene hothouse climate was creating opportunities that had never existed before. Tropical forests extended almost to the poles. Ocean temperatures were warm enough to support coral reefs in places that are now frozen tundra. Atmospheric CO2 levels were multiple times higher than they are today, creating a greenhouse effect that turned Earth into a biological laboratory. But this hothouse world couldn't last forever, bored people. And when it ended dramatically, setting up the next phase of mammalian evolution. Because the late Eocene was when Earth's climate system hit another inflection point. When the long, slow cooling that would eventually lead to ice ages began in earnest. The transition from the Eocene to the Oligocene wasn't as sudden or dramatic as the asteroid impact that ended the dinosaurs, but it was just as transformative for mammalian evolution. As temperatures dropped and climates became more seasonal, mammals had to adapt once again. The giants of the Eocene couldn't all survive in a cooler, drier world. The tropical forests shrank, grasslands expanded, and mammals found themselves in yet another new world that demanded new solutions. But that's a story for what comes next, as we follow mammals through their next great transformation. Because if the Paleocene was about survival and the Eocene was about experimentation, then the Oligocene was about specialization. It was when mammals stopped trying to be everything to everyone and started getting really, really good at specific ways of life. And some of those specializations would lead directly to the mammals we know today, including the one species that would eventually become curious enough to dig up fossils and piece together this incredible story of planetary recovery and biological innovation. Stay with me, because we're about to enter the epoch when mammals learned that sometimes the key to success isn't getting bigger or weirder or more experimental. Sometimes it's about finding your niche and perfecting it, even if that niche is something as specific as large herbivore that runs really fast across open grasslands, or small primate that uses tools and lives in complex social groups. The age of mammalian gigantism was coming to an end, but the age of mammalian genius was just beginning. The Oligocene epoch, bored people, was when mammals basically looked at their Eocene party phase and said, okay, that was fun, but maybe it's time to get our act together. We're talking about the period from 34 to 23 million years ago, when the planet's climate decided to throw the ultimate buzzkill at mammalian evolution. The hothouse world was ending, temperatures were dropping, and suddenly all those experimental giants and tropical weirdos had to figure out how to survive in a world that was getting colder, drier, and significantly less forgiving. But here's the thing about evolutionary pressure. It doesn't just kill off the failures, it forces the survivors to become absolutely brilliant at whatever they do. And that's exactly what happened during the Oligocene. Mammals stopped trying to be everything and started getting really, really good at being specific things. This was the epoch when our ancestors learned that specialization, not size, was the key to long-term success. Picture the world 30 million years ago, and the first thing you'd notice is that it looks more familiar than anything we've talked about so far. The palm trees are gone from the Arctic. The tropical forests have retreated toward the equator. In their place, you're seeing something that the planet had never really experienced before. Vast grasslands stretching to the horizon. Not the dense, humid forests of the Eocene, but open savannas and prairies where you can see for miles in every direction. This shift from forest to grassland was one of the most important ecological transitions in Earth's history, and it happened because of a cascade of climate changes that started in the late Eocene. As global temperatures dropped, rainfall patterns shifted. Many areas that had been wet enough to support dense forests became too dry. The massive trees that had dominated terrestrial ecosystems for millions of years gave way to grasses, herbs, and scattered woodlands. And grasses, it turns out, are evolutionary game changers. Unlike trees, which invest most of their energy in growing tall and living for decades or centuries, grasses put their energy into rapid growth and reproduction. They can sprout up quickly after being eaten, trampled, or burned. They spread horizontally through underground root systems. They're basically the biological equivalent of fast food, high energy, quick turnover, available in large quantities. But here's the catch. Grass is incredibly hard to digest. It's full of silica, which wears down teeth like sandpaper. It's low in protein and high in cellulose, which most animals can't break down efficiently. To make a living eating grass, you need some serious biological modifications. You need teeth that can handle the abrasive material. You need guts that can process cellulose. You need metabolisms that can extract nutrients from low-quality food. The mammals that figured this out first were about to inherit the Earth. Enter the ungulates, the hoofed mammals. During the Oligocene, these animals underwent one of the most spectacular adaptive radiations in mammalian history. They looked at these vast new grasslands and said, "Challenge accepted." And then they proceeded to evolve some of the most sophisticated digestive systems, dental arrangements, and locomotory adaptations that vertebrates have ever developed. Take the early horses, for example. In the Eocene, horses were tiny forest creatures about the size of house cats, with multiple toes and teeth designed for eating soft leaves and fruits. But as grasslands expanded, horses began one of the most dramatic evolutionary transformations ever documented. They got bigger, developing longer legs for covering vast open distances. They lost most of their toes, eventually ending up with a single hoof that was perfect for running on hard ground. And their teeth became grinding machines, constantly growing throughout their lives to compensate for the wear caused by eating abrasive grass. But the real innovation was in their digestive systems. Horses developed massive cecums, essentially fermentation chambers, in their intestines where bacteria could break down cellulose. They became living bioreactors, using microbial partners to extract nutrients from plant material that would have been inedible to their ancestors. And they weren't alone. All across the grasslands of the Oligocene, different mammalian lineages were independently discovering the secrets of herbivory. Early camels were developing their own solutions to the grass problem. Early rhinoceroses were becoming specialized browsers and grazers. The ancestors of deer, antelope, and cattle were figuring out the most sophisticated digestive system ever evolved, the ruminant gut. Ruminants, bored people, are basically walking fermentation factories. They have 4-chambered stomachs that worked like a biological brewery, using different species of bacteria and protozoa to break down plant material in stages. They can literally eat grass, let their microbial partners pre-digest it, regurgitate it, chew it again, and then send it through additional fermentation chambers. It's gross, it's complicated, and it's absolutely brilliant. This system was so successful that ruminants quickly became the dominant large herbivores on most continents. They could extract more nutrition from low-quality plant material than any other animals, which meant they could survive in environments that would starve other mammals. They were the mammalian equivalent of hybrid cars, incredibly efficient at converting available resources into usable energy. But all of this herbivorous innovation created a new problem. If you suddenly have vast herds of large, meaty herbivores wandering around open grasslands, something is going to evolve to eat them. And that something was about to revolutionize mammalian predation. The Oligocene was when mammals perfected the art of the hunt. Not the ambush predation of crocodiles or the opportunistic scavenging that had characterized earlier mammalian carnivores, but coordinated, intelligent pursuit predation. This was when mammals learned to run down their prey across open country, using endurance, strategy, and social cooperation. The early cats were among the first to figure this out. During the Oligocene, the cat family split into two major lineages that would dominate mammalian predation for the next 30 million years. There were the saber-toothed cats, which specialized in taking down massive herbivores with oversized canine teeth that could deliver killing bites to thick-skinned giants. And there were the conical-toothed cats, the ancestors of all modern felines, which developed the kind of precision killing techniques that make house cats such effective hunters. But cats weren't the only predators getting creative. The dog family was also undergoing rapid diversification during the Oligocene, experimenting with pack hunting, endurance running, and the kind of complex social behaviours that would eventually make wolves one of the most successful predators on the planet. And then there were the hyenodonts, those weird mammalian carnivores that weren't related to any modern predator family. These were the last holdouts from the Eocene world of experimental predation, and some of them were absolute monsters. Hyenodon gigas was a predator the size of a grizzly bear, with jaws that could crack the bones of the largest Oligocene herbivores. These things were the apex predators of their time, the mammalian equivalent of tyrannosaurs. But here's what's fascinating about Oligocene predation. It wasn't just about being big and scary anymore. It was about being smart. Predators were developing more sophisticated hunting strategies, better coordination within groups, more complex communication systems. They were learning to read the behavior of their prey, to anticipate migration patterns, to exploit the weaknesses of the new grassland ecosystems. Meanwhile, the herbivores were developing equally sophisticated anti-predator strategies. They were evolving better senses, faster running speeds, more effective group defense behaviors. The Oligocene grasslands became evolutionary arms races, with predators and prey constantly pushing each other to new levels of performance. And in the middle of all this grassland drama, something else was happening that would ultimately matter more than any individual predator-prey relationship. Mammals were developing the kind of complex social behaviours that would eventually lead to intelligence, culture, and civilization. The early primates of the Oligocene were still small, still arboreal, still living in the shrinking forests rather than the expanding grasslands. But they were facing their own evolutionary pressures that were pushing them toward greater social complexity. As forests became more fragmented, primate groups had to travel longer distances between food sources. They had to remember the locations of fruit trees across larger territories. They had to coordinate group movements more effectively. These pressures were selecting for larger brains, better memory, more sophisticated communication. Early Oligocene primates were developing the cognitive toolkit that their descendants would eventually use to make tools, control fire, and figure out how to survive in every habitat on Earth. But primate intelligence wasn't the only kind of mammalian intelligence evolving during the Oligocene. In the oceans, whales were developing their own form of genius. The fully aquatic whales of the Oligocene were experimenting with echolocation, complex vocalizations, and the kind of social behaviours that would eventually make them some of the most intelligent animals on the planet. Early baleen whales were figuring out how to filter feed on massive swarms of small organisms, developing feeding strategies that could support body sizes larger than any terrestrial animal. Early toothed whales were becoming sophisticated hunters, using sound to navigate and hunt in the dark depths of the ocean. And on land, other mammalian lineages were developing their own forms of intelligence. Early elephants were evolving the complex social structures and long-term memory that make modern elephants some of the most emotionally sophisticated animals alive. Early bats were perfecting echolocation systems that are more precise than any human-made sonar. Early rodents were developing the kind of adaptability and problem-solving skills that would eventually make them the most successful mammalian group on the planet. But perhaps the most important development of the Oligocene wasn't happening in any single species or lineage. It was happening at the ecosystem level. For the first time since the extinction of the dinosaurs, terrestrial ecosystems were becoming truly complex again. Not the simple predator-prey relationships of the early Paleocene, not the experimental chaos of the Eocene, but sophisticated, multi-layered communities with dozens of species filling specialized ecological roles. These Oligocene ecosystems were the first to really resemble modern ones. You had large herbivores filling different grazing niches. You had predators specialized for hunting different types of prey. You had small mammals filling roles as seed dispersers, pollinators, and ecosystem engineers. You had the beginnings of the kind of ecological complexity that characterizes the natural world today. And all of this complexity was being driven by one fundamental change. Mammals had learned to live in the open. For 100 million years, mammalian evolution had been constrained by the need to hide, to stay small, to avoid being noticed by the giant reptiles that ruled the world. But in the Oligocene, mammals finally stepped out of the shadows and claimed the open spaces of the planet. Grasslands were mammalian territory in a way that forests had never been. In dense woods, you're always just a few feet away from cover, from hiding places, from escape routes. But on open grasslands, you're exposed. You can see for miles, but so can everything else. Success in this environment required new strategies. Speed instead of stealth, cooperation instead of solitary behaviour, intelligence instead of instinct. The mammals that thrived in the Oligocene grasslands were the ones that could think ahead, that could coordinate with others of their kind, that could adapt to changing conditions. They were developing the cognitive and social tools that would eventually allow mammals to dominate not just terrestrial ecosystems but the entire planet. By the end of the Oligocene, the mammalian world was looking remarkably modern. The major groups were all in place. Ungulates dominating the grasslands, carnivores hunting them, primates in the trees, whales in the oceans, bats in the air, rodents everywhere. The age of experimental giants was over. The age of specialised, intelligent, socially complex mammals had begun. But we're still not at the end of this story, bored people. Because what came next was when mammals took all of these Oligocene innovations, the specialisation, the intelligence, the social complexity, and pushed them to their absolute limits. The Miocene epoch was when mammals became the most diverse, successful, and downright incredible group of animals that had ever lived on Earth. And it was also when one particular lineage of primates began the evolutionary journey that would eventually lead to creatures capable of looking back through deep time and understanding their own origins. Creatures that could piece together the story of how life recovered from the worst catastrophe in Earth's history and turned it into the greatest comeback story ever told. Stay with me as we dive into the age when mammals reached their peak, when grasslands covered continents, when intelligence began its long climb toward consciousness, and when the stage was finally set for the emergence of the one species that would eventually question everything, including its own place in the grand story of life on Earth. The Miocene epoch, bored people, was when mammals looked at everything they'd accomplished in the previous 30 million years and said, you know what, let's do all of that, but bigger, smarter, and with significantly more attitude. We're talking about the period from 23 to 5 million years ago, when mammalian evolution basically went into overdrive and produced some of the most spectacular, diverse, and downright ridiculous creatures that have ever walked, swum, or flown across this planet. This was peak mammal, the golden age of warm-blooded milk-producing vertebrates. If you could somehow time travel to the middle Miocene about 15 million years ago, you'd find yourself in a world that was both familiar and completely alien. Familiar because the basic structure was there. Grasslands, forests, predators, prey, all the ecological relationships we recognise today. But alien because everything was cranked up to 11. Picture this. You're standing on the Great Plains of North America, except they're not plains yet. They're vast savannas stretching from Canada to Mexico. The grass is taller than you are, waving in hot winds that carry the scent of dust and distant storms. And moving through that grass are herds of animals that make the modern African savanna look like a petting zoo. There are horses, but not the horses you know. These are three-toed Hipparion, about the size of modern horses but built like biological race cars, with longer legs, more flexible spines, and an attitude that says they were born to run. They move in herds of thousands, their hoofbeats creating thunder that can be heard for miles. When they run, the ground shakes like an earthquake. And they need to run, because hunting them are predators that make modern big cats look like house pets. Amphimachiridas, a saber-toothed cat the size of a lion, but with canine teeth 8 inches long, stalks through the tall grass like a furry nightmare. These things didn't just kill their prey, they punctured major arteries with surgical precision, then waited for massive herbivores to bleed out. They were living syringes with claws, and they were absolutely terrifying. But the horses and cats were just the opening act. The real stars of the Miocene megafauna were creatures that pushed the boundaries of what it meant to be a mammal. Take the Chalicotheres, for example. These were animals that looked like someone had taken a horse, given it the claws of a giant sloth, and then asked it to spend most of its time sitting on its haunches like a bear. They were knuckle-walking herbivores that used their massive claws to pull down tree branches, living proof that evolution sometimes gets really creative when it's bored. Or consider Dinotherium, an elephant that decided regular elephant tusks weren't dramatic enough. Instead of tusks that curved upward and forward, Dinotherium had tusks that curved downward from its lower jaw, making it look like some kind of prehistoric walrus-elephant hybrid. These things were the size of modern elephants, but with the proportions of something designed by a committee that couldn't agree on what an elephant should look like. But perhaps the most mind-bending creatures of the Miocene were the giant ground sloths. We're not talking about the cute, slow-moving tree sloths you see in nature documentaries. We're talking about Megatherium, a creature the size of a small elephant that could rear up on its hind legs and tower 12 feet in the air. These things had claws like scimitars and the muscle mass to rip apart trees, but they used all that size and strength to eat leaves. They were basically living bulldozers powered by vegetation, and they were absolutely magnificent. And that was just North America. In South America, which had been isolated from the other continents, for most of the Cenozoic, mammals had been conducting their own evolutionary experiments in complete isolation. The results were spectacular and weird in ways that make the rest of the Miocene look conservative. There were terror birds, flightless predators that stood 8 feet tall and had beaks that could crack skulls like eggs. Phorus racos was basically what you'd get if you took a modern cassowary, made it twice as large, gave it the hunting instincts of a wolf, and then let it loose on a continent full of mammals that had never seen anything like it. These birds were the apex predators of South America for millions of years, proving that mammals weren't the only vertebrates getting creative in the post-dinosaur world. There were also giant rodents, and when I say giant, I mean Joseph Artegasia, a rodent the size of a buffalo with teeth that never stopped growing. Imagine a capybara that weighs as much as a small car, and you're getting close to what these things looked like. They were living lawnmowers, grazing their way across South American grasslands, and probably not caring much about anything that couldn't bite through their thick hides. But the real innovation of the Miocene wasn't happening in terms of size or weirdness. It was happening in terms of intelligence and social complexity. This was when mammals began developing the kind of sophisticated behaviours that would eventually lead to culture, technology, and the ability to completely reshape planetary ecosystems. The early apes of the Miocene were conducting their own revolution in the forests of Africa and Eurasia. These weren't the small generalised primates of earlier epochs. These were large, intelligent, socially complex animals that were experimenting with new ways of moving through the world and interacting with their environment. Proconsul, one of the best-known Miocene apes, was about the size of a modern chimpanzee, but with a more flexible body plan that allowed for both arboreal and terrestrial locomotion. These animals were developing the kind of problem-solving abilities that would eventually allow their descendants to make tools, control fire, and develop language. They weren't there yet, but they were laying the cognitive groundwork. More importantly, they were developing complex social structures that required sophisticated communication, memory, and emotional intelligence. Miocene ape societies were likely similar to those of modern great apes, complex networks of alliances, hierarchies, and relationships that required individuals to keep track of who was allied with whom, who could be trusted, and who might be a threat. This kind of social complexity was a major driver of brain evolution. Living in a group where your survival depends on your ability to navigate complicated social relationships is cognitively demanding in ways that simple predator-prey interactions aren't. You need to be able to remember past interactions, predict future behaviour, communicate complex information, and coordinate group activities. These pressures were selecting for larger brains, better memory, and more sophisticated cognitive abilities. But primates weren't the only mammals developing greater intelligence during the Miocene. In the oceans, whales were pushing the boundaries of what it meant to be a smart mammal. The first truly modern whales appeared during this epoch, animals with brain sizes and social behaviours that rivaled those of terrestrial mammals. Early sperm whales were developing the largest brains that had ever existed on Earth, with complex neural structures that supported sophisticated echolocation, long-range communication, and probably forms of culture that we're only beginning to understand. These animals were living in social groups that spanned ocean basins, communicating across hundreds of miles and passing behavioural traditions from generation to generation. Meanwhile, the early baleen whales were perfecting filter feeding strategies that allowed them to grow to sizes that dwarfed even the largest dinosaurs. Blue whales, the largest animals that have ever lived, trace their lineage back to the Miocene innovations in whale feeding behaviour. These animals figured out how to extract enormous amounts of energy from tiny organisms, supporting body masses that push the physical limits of what's possible for a vertebrate. On land, other mammalian lineages were developing their own forms of intelligence and social complexity. Early elephants were evolving the sophisticated memory and emotional behaviours that make modern elephants some of the most psychologically complex animals on the planet. These animals were developing culture, learned behaviours passed down through generations, complex mourning rituals, and social structures that could span decades and hundreds of individuals. The carnivores were getting smarter too. Early members of the dog family were perfecting pack hunting strategies that required coordination, communication, and the ability to plan attacks on prey much larger than any individual pack member. These animals were developing the kind of cooperative behaviours that would eventually make wolves one of the most successful predators on Earth. But perhaps the most significant development of the Miocene was happening at the ecosystem level. This was when grasslands truly came to dominate terrestrial landscapes, creating the kind of open environments that would select for the traits that eventually led to human evolution. The expansion of grasslands during the Miocene was driven by continued climate cooling and the evolution of grasses themselves. C4 grasses, a more efficient type of grass that could thrive in drier, more seasonal climates, began to dominate many regions. These grasses were better at extracting carbon dioxide from the atmosphere and more resistant to drought, fire, and grazing pressure. As grasslands expanded, they created new selective pressures for the animals that lived in them. Open environments favoured speed over stealth, endurance over strength, social cooperation over individual competition. Animals that could coordinate their behaviour, communicate over long distances, and adapt to changing conditions had enormous advantages. This was particularly true for the herbivores. Living on open grasslands meant being constantly exposed to predators, which selected for animals that could work together to detect threats and coordinate defensive responses. Herd behaviour became increasingly sophisticated, with different species developing complex alarm systems, coordinated movement patterns, and mutual defence strategies. The predators, in turn, had to become more intelligent and cooperative to succeed against these well-defended prey animals. Pack hunting became more common, with different carnivore species developing increasingly sophisticated strategies for taking down large, dangerous prey animals. All of this was creating feedback loops that pushed mammalian intelligence and social complexity to new levels. Animals that could think ahead, communicate effectively, and work together had enormous advantages in these complex ecosystems. Brain sizes were increasing across multiple mammalian lineages, not just in primates, but in carnivores, ungulates, proboscideans, and cetaceans. But the Miocene wasn't just about individual species getting smarter. It was also about ecosystems becoming more complex and interconnected. The grassland ecosystems of the Miocene were some of the most diverse and productive that had ever existed on land. They supported incredible diversity of herbivores, which in turn supported diverse predator communities which created complex webs of ecological relationships. These ecosystems were also incredibly dynamic. Climate variability during the Miocene meant that grasslands expanded and contracted, forests appeared and disappeared, and animal populations had to constantly adapt to changing conditions. This environmental variability was a major driver of evolutionary innovation, selecting for animals that could be flexible, adaptable, and capable of learning from experience. By the late Miocene, around 8 million years ago, the stage was set for the next major chapter in mammalian evolution. The climate was continuing to cool and dry, grasslands were expanding even further, and the selective pressures that would eventually lead to human evolution were intensifying. In the forests of Africa, early hominins were beginning to experiment with bipedal locomotion, possibly as an adaptation to increasingly fragmented woodland environments. These animals weren't human yet, but they were developing the traits that would eventually allow their descendants to walk upright, make tools, and develop the kind of intelligence that could understand their own evolutionary history. But that's getting ahead of ourselves, bored people, because the late Miocene had one more surprise in store, one more dramatic shift that would reshape mammalian evolution and set up the conditions for everything that followed. The climate was about to get serious about cooling down. Ice was going to start forming at the poles again for the first time in 30 million years, and mammals were going to have to adapt to a world that was becoming increasingly cold, dry, and challenging. The age of mammalian abundance was coming to an end, but the age of mammalian ingenuity was just beginning. Because what came next would push our ancestors to develop the kinds of adaptations, intelligence, tool use, social cooperation, cultural transmission that would eventually allow one species of mammal to become so successful that it could reshape the entire planet. Stay with me as we head into the Pliocene, the epoch when ice returned to Earth, when grasslands reached their maximum extent, and when one particular lineage of African apes began the evolutionary journey that would eventually lead to creatures capable of building cities, writing symphonies, and launching rockets to the moon. The story of how mammals recovered from the dinosaur extinction was about to culminate in the emergence of the one species that would eventually question everything, including its own place in the grand narrative of life on Earth. The Pliocene epoch, bored people, was when Earth decided to throw mammals the ultimate curveball. We're talking about the period from 5.3 to 2.6 million years ago, when our planet looked at 30 million years of warm, stable, mammal-friendly climate and said, you know what, let's make this interesting. Ice was coming back to the poles for the first time since the Eocene. Temperatures were dropping and mammals were about to face their biggest challenge since that asteroid turned the Cretaceous into ancient history. But here's the thing about evolutionary pressure. It doesn't just weed out the weak. It forces the survivors to become absolutely brilliant at staying alive. And that's exactly what happened during the Pliocene. This wasn't just another climate shift. This was the epoch when mammals learned that intelligence, not size or strength or even specialization, was the ultimate survival strategy. Picture the world 4 million years ago, and the first thing you'd notice is that it's getting crowded. Not with people. We're still a few million years away from that particular experiment, but with mammals that had figured out how to squeeze every possible advantage from their environment. The Miocene had been the age of mammalian abundance, when there was room for giant ground sloths and saber-toothed cats the size of lions. The Pliocene was the age of mammalian efficiency, when only the smartest, most adaptable, most socially sophisticated animals could make it. The grasslands were reaching their maximum extent, covering vast swathes of every continent except Antarctica. But these weren't the lush, productive savannas of the Miocene. These were drier, more seasonal, more unpredictable. The climate was becoming increasingly variable, with ice ages beginning to cycle on and off, like some kind of planetary thermostat gone haywire. Animals that could adapt quickly to changing conditions had enormous advantages. Animals that couldn't were about to become fossils. And in the middle of all this climatic chaos, something extraordinary was happening in the woodlands of Eastern Africa. A group of apes was conducting an evolutionary experiment that would eventually change everything. They weren't trying to get bigger like the Miocene giants. They weren't trying to get more specialized like the Oligocene grazers. They were trying something completely different. They were trying to get smarter. These early hominins, creatures like Australopithecus afarensis, the species that gave us the famous Lucy fossil, were dealing with a problem that no mammal had ever faced before. Their forest homes were fragmenting, breaking up into isolated patches, separated by expanding grasslands. To survive, they needed to travel longer distances between food sources, often across open country, where they were exposed to predators that could kill them without breaking stride. The solution they came up with was unprecedented in mammalian evolution. They started walking upright. Not occasionally, not just when they needed to see over tall grass, but as their primary mode of locomotion. They were literally rising above their quadrupedal past, freeing their hands for new possibilities, while their feet carried them across landscapes that would have terrified their ancestors. Now, bipedalism might not sound revolutionary to you, bored people, because you've been doing it your entire life without thinking about it. But from an evolutionary perspective, learning to walk on two legs is absolutely insane. It's mechanically inefficient compared to quadrupedal locomotion. It makes you slower, less stable, more vulnerable to back problems. It complicates childbirth because upright pelvises are narrower than quadrupedal ones. By most measures, bipedalism should have been an evolutionary dead end, but it wasn't, because it came with one crucial advantage that outweighed all the disadvantages. It freed the hands, and hands that weren't needed for locomotion could be used for other things, carrying food over long distances, manipulating objects, making tools, and eventually, much later, building civilizations. The early hominins weren't there yet, of course. Lucy and her contemporaries were still essentially upright apes, with brain sizes barely larger than modern chimpanzees. But they were laying the groundwork for everything that came later. They were developing the anatomical and behavioural foundation that would eventually support intelligence, culture, and technology. And they weren't the only mammals getting creative during the Pliocene. All across the planet, animals were adapting to the new climatic reality in ways that would have seemed impossible just a few million years earlier. In North America, the great grassland ecosystems were reaching their peak diversity and complexity. Herds of horses, camels, and pronghorns moved across plains that stretched from horizon to horizon, followed by predators that had perfected the art of cooperative hunting. Early wolves were developing pack behaviours that allowed small predators to take down prey many times their size. Saber-toothed cats were refining their killing techniques to target the most vulnerable spots on increasingly well-defended herbivores. But the real innovation was happening in terms of migration and seasonal adaptation. As climates became more variable, many mammals developed the ability to move vast distances in response to changing conditions. This wasn't just the random wandering of earlier epochs. This was coordinated, purposeful migration that required sophisticated navigation abilities, social coordination, and the kind of long-term planning that pushed mammalian intelligence to new levels. The American cheetah, yes, North America had its own species of cheetah during the Pliocene, was probably the fastest land animal that ever lived, capable of speeds that would make modern cheetahs look like they were jogging. These cats had evolved to hunt pronghorns that could run at 60 miles per hour for extended distances. It was an evolutionary arms race played out at highway speeds across the Great Plains. Meanwhile, in the oceans, whales were pushing the boundaries of what it meant to be an intelligent mammal. The first truly modern whale societies were emerging during the Pliocene, complex social structures that spanned ocean basins and probably involved forms of culture that we're only beginning to understand. These animals were developing dialects, teaching hunting techniques to their young, and possibly even creating the kind of oral traditions that anthropologists typically associate with human societies. Orcas, the apex predators of the marine world, were perfecting cooperative hunting strategies that rivaled anything terrestrial predators had developed. Different populations were specializing in hunting different types of prey, developing distinct techniques that were passed down through generations. Some pods focused on hunting fish, others on marine mammals, still others on sharks. Each had its own hunting traditions, communication patterns, and social structures. But perhaps the most remarkable development of the Pliocene was happening among the elephants. The proboscideans of this epoch were developing some of the most sophisticated social behaviours and emotional intelligence that had ever evolved in a non-primate mammal. Early mastodons and mammoths were living in complex matriarchal societies where knowledge was passed down through generations, where individuals could recognise dozens of family members, and where death was met with behaviours that can only be described as mourning. These elephants were developing culture in the truest sense of the word, learned behaviours that varied between populations and were transmitted socially rather than genetically. Different herds had different migration routes, different feeding strategies, different ways of dealing with threats. They were creating traditions that could persist for centuries, passed down from mothers to daughters in an unbroken chain of mammoth memory. And in the rapidly cooling northern regions, a completely different kind of mammalian adaptation was taking place. As temperatures dropped and ice began to form, mammals were developing the physiological and behavioural adaptations that would eventually allow them to survive full-scale ice ages. Early woolly mammoths were experimenting with the combination of size, insulation, and social behaviour that would make them the iconic megafauna of the Ice Age world. These weren't just large elephants with fur, they were biological furnaces, maintaining body temperatures in conditions that would kill most mammals. They were developing specialised blood circulation patterns, counter-current heat exchange systems, and behavioural adaptations that allowed them to find food under snow and ice. Arctic foxes, wolves, and other cold-adapted mammals were perfecting the kind of seasonal behaviour changes that would allow them to thrive in environments where summer and winter were like completely different planets. These animals were developing the ability to change their metabolism, their fur density, their hunting strategies, even their social structures in response to dramatic seasonal changes. But the Pliocene wasn't just about individual species adapting to climate change. It was also about entire ecosystems reorganising themselves in response to new conditions. The complex grassland communities of the Miocene were giving way to simpler, more robust ecosystems that could survive increasing climatic variability. This ecosystem simplification was actually a form of evolutionary preparation for the ice ages that were coming. Complex ecosystems with many specialised species are vulnerable to disruption when conditions change rapidly. Simpler ecosystems with fewer, more adaptable species are more likely to survive dramatic environmental shifts. The mammals that thrived during this transition were the ones that could be flexible, that could adapt their behaviour and diet in response to changing conditions, that could work together to solve problems that no individual could handle alone. Intelligence, memory, and social cooperation were becoming the most valuable traits in the mammalian toolkit, and nowhere was this more evident than in the continuing evolution of the African hominins. By the late Pliocene, around 3 million years ago, these upright apes were beginning to show signs of the cognitive revolution that would eventually lead to human civilization. Their brain sizes were starting to increase, not dramatically, but consistently. Their tool use was becoming more sophisticated, progressing from opportunistic rock throwing to deliberate stone modification. More importantly, they were developing the kind of complex social structures that would eventually support culture, language, and technology. Early hominin societies were probably similar to those of modern great apes, but with additional layers of complexity made necessary by their ground-dwelling, group-travelling lifestyle. They needed to coordinate movement across dangerous open country, share information about distant food sources, and work together to defend against predators that could easily kill any individual. These social pressures were selecting for bigger brains, better communication abilities, and more sophisticated cognitive skills. The hominins weren't just adapting to climate change, they were developing the mental tools that would eventually allow them to control their environment rather than simply respond to it. But we're getting ahead of ourselves, bored people, because the Pliocene had one more surprise in store. Around 2.6 million years ago, the planet's climate system crossed a threshold that would define the rest of mammalian evolution. The ice ages were about to begin in earnest, and mammals were going to face the ultimate test of their adaptability. The Pleistocene epoch was coming, bringing with it glacial cycles that would make the climate variability of the Pliocene look like minor fluctuations. Ice sheets would advance and retreat across entire continents. Sea levels would rise and fall by hundreds of feet. Entire ecosystems would appear and disappear as conditions changed more rapidly than they had in millions of years. And in the middle of this climatic chaos, one particular lineage of African apes would continue their evolutionary experiment with intelligence, eventually producing creatures capable of making fire, crafting sophisticated tools, developing language, and creating the kind of complex societies that could survive almost any environmental challenge. The age of mammalian giants was long over. The age of mammalian specialists had run its course. What was coming next was the age of mammalian genius, when one species would become so intelligent, so adaptable, so successful at manipulating its environment that it would eventually spread to every continent, reshape entire ecosystems, and develop the cognitive abilities necessary to understand its own evolutionary history. But that transformation wouldn't happen overnight. It would take another 2 million years of ice ages, climate swings, and evolutionary pressure before our ancestors would develop the full suite of abilities that define modern humans. The journey from Lucy to Einstein was just beginning, and it would be the most remarkable transformation in the history of life on Earth. Stay with me as we head into the Pleistocene, the epoch of ice and innovation, when mammals would face their greatest challenge since the asteroid impact and respond by producing the most intelligent, creative, and ultimately successful species that had ever lived. Because what happened next wasn't just the end of the mammalian recovery from the dinosaur extinction. It was the beginning of something entirely new in the history of life on our planet. The story of how Earth rebooted after the dinosaur apocalypse was about to culminate in the emergence of creatures capable of not just surviving in the world, but of completely remaking it according to their own design. And those creatures, bored people, were us. The Pleistocene epoch bored people was when Earth decided to put mammals through the ultimate stress test. We're talking about the period from 2.6 million years ago to about 11,700 years ago, when our planet basically turned into a cosmic mood ring, cycling between freezing and thawing with the regularity of someone who can't decide what temperature to set their thermostat. Ice ages came and went like seasonal depression, except each cycle lasted tens of thousands of years and reshaped entire continents. Picture this: massive ice sheets, some over a mile thick, grinding their way across North America and Europe like planetary bulldozers made of frozen water. These weren't just big snowdrifts bored people. These were geological forces that carved out the Great Lakes, scraped the tops off mountains, and turned entire regions into moonscapes of scraped bedrock. And then, just when life figured out how to deal with all that ice, it would melt away, flooding coastlines and creating entirely new landscapes. But here's where the story gets really interesting. Because mammals didn't just survive these ice age cycles, they used them as evolutionary boot camps. The constant climate upheaval created a planet-wide laboratory for testing new survival strategies, and the results were absolutely spectacular. The mammals that emerged from this frozen crucible weren't just bigger or stronger than their predecessors. They were smarter, more social, more adaptable. They had learned to thrive in conditions that would have sent their Miocene ancestors running for the hills, if there had been any hills left that weren't buried under glaciers. Take the woolly mammoth, for example. This wasn't just an elephant with a fur coat. This was a biological masterpiece, engineered for survival, in conditions that would kill most modern animals within hours. These creatures had blood that functioned like antifreeze, ears that were perfectly sized to prevent heat loss, and social behaviours so sophisticated that they could coordinate herd movements across thousands of miles of tundra. Mammoth societies were like nomadic universities where knowledge about migration routes, seasonal patterns and survival techniques was passed down through generations of matriarchs who could live for 60 years or more. They developed what can only be called culture. Different herds had different migration patterns, different feeding strategies, different ways of dealing with predators and environmental challenges. And they weren't alone in this evolutionary arms race against the ice. Across the northern continents, mammals were developing increasingly sophisticated adaptations for life in a world where summer and winter were like visits to different planets. Saber-toothed cats reached their peak during the Pleistocene, but not the ones you're probably imagining. Smilodon fatalis was a predator that made modern big cats look like house pets. We're talking about an animal with the build of a lion, the killing power of a great white shark, and canine teeth that were literally designed for puncturing the thick hides and massive neck muscles of Ice Age megafauna. But here's what makes Smilodon so fascinating. Recent research suggests these cats were highly social, possibly living in family groups and cooperating to take down prey that no individual predator could handle alone. They were developing pack hunting strategies that combined the stealth of cats with the coordination of wolves, creating predatory societies that could target animals the size of small elephants. Meanwhile, the actual wolves were conducting their own evolutionary experiments in social cooperation. Pleistocene wolves were larger than their modern descendants, but more importantly, they were smarter. They were developing the kind of complex pack dynamics that allowed small predators to coordinate attacks on prey many times their size. They were learning to communicate across vast distances, to plan hunting strategies that could unfold over days or weeks, to care for injured pack members and raise communal young. These wolf societies were becoming so sophisticated that they started attracting the attention of another species that was also experimenting with social cooperation and pack hunting. But we'll get to those particular apes in a moment, because first we need to talk about what was happening to the planet itself during these Ice Age cycles. The Pleistocene wasn't just cold, it was chaotic. Climate didn't just change, it oscillated wildly between extremes. Within the span of a few thousand years, regions would go from tropical to Arctic and back again. Forests would appear and disappear. Coastlines would advance and retreat by hundreds of miles. Entire ecosystems would assemble, thrive, and then vanish as conditions shifted faster than evolution could keep up. This environmental chaos was creating something that had never existed before in Earth's history: a planetary laboratory for testing adaptability. Animals that could only survive in specific conditions were constantly going extinct. Animals that could adapt quickly to changing environments were thriving like never before. And the most adaptable animals of all were developing something unprecedented: the ability to change their environment rather than just adapting to it. They were learning to make fire, build shelters, craft tools, and create the kind of artificial environments that could buffer them against even the most extreme climate swings. These animals, bored people, were our ancestors, and during the Pleistocene, they were about to make the leap from being just another species of clever ape to becoming something entirely new in the history of life on Earth. The early humans of the Pleistocene, species like Homo erectus, Homo neanderthalensis, and eventually Homo sapiens, were conducting the most audacious evolutionary experiment in mammalian history. They weren't just adapting to their environment through biological changes that took thousands of generations. They were adapting through cultural innovations that could spread through entire populations within a single generation. When the climate got colder, they didn't wait for evolution to give them thicker fur. They invented clothing. When food became scarce, they didn't develop more efficient digestive systems. They invented cooking, which made previously inedible foods nutritious and dramatically reduced the energy costs of digestion. When predators threatened them, they didn't evolve bigger teeth or stronger muscles. They invented weapons that could kill animals many times their size. This was a completely new form of evolution, not biological, but cultural. And it was happening at speeds that would have seemed impossible to any previous species. Within just a few 100,000 years, these early humans went from using simple stone tools to creating sophisticated hunting equipment, artistic traditions, and social structures that could coordinate the activities of hundreds of individuals. But the real breakthrough came when they learned to control fire. Not just use it opportunistically when they found it burning naturally, but actually create it on demand. This single innovation transformed them from just another mammalian species into ecosystem engineers capable of reshaping entire landscapes. With fire, early humans could extend their daily activity into the hours of darkness, when most predators were most active. They could cook food, which made more calories available and reduced the risk of disease. They could stay warm in climates that would otherwise be uninhabitable. They could clear forests, manage grasslands, and even hunt by driving prey animals into controlled burns. Fire was the technology that allowed humans to break free from the ecological constraints that limited every other mammalian species. With fire, they could live in environments From the Arctic tundra to tropical rainforests, they could hunt animals that were faster, stronger, and more dangerous than they were. They could preserve food for lean times and share resources across extended social networks. But perhaps most importantly, fire created the social conditions that would eventually lead to language, art, and culture. Gathering around fires in the evening created opportunities for extended social interaction that no other mammalian species had ever experienced. These firelit gatherings became the venues where knowledge was shared, stories were told, and the kind of complex cultural traditions were developed that would eventually allow humans to accumulate knowledge across generations. By the late Pleistocene, around 50,000 years ago, humans had developed all the basic capabilities that define our species today. They were making sophisticated tools, creating art, burying their dead with ceremony, and living in complex social groups that could coordinate activities across vast territories. They had become the first species in Earth's history capable of cultural evolution, the ability to improve their survival strategies through learning and innovation rather than just genetic adaptation. And they were about to put these capabilities to the ultimate test, because the Pleistocene was ending with one final climate upheaval that would reshape the planet one more time. The last ice age was coming to an end, but not gradually. The transition to our current interglacial period happened with shocking speed, creating environmental changes that were more dramatic than anything mammals had faced since the asteroid impact. Within just a few thousand years, massive ice sheets melted, sea levels rose by hundreds of feet, and entire ecosystems collapsed or were completely transformed. Many of the Pleistocene megafauna, the giant ground sloths, saber-toothed cats, woolly mammoths, and cave bears that had dominated Ice Age ecosystems, went extinct during this transition. But humans not only survived this environmental catastrophe, they thrived during it. They used their cultural adaptations to exploit the new opportunities created by changing climates. They developed agriculture, which allowed them to support much larger populations than had ever been possible for a mammalian species. They built permanent settlements, which became the foundation for increasingly complex societies. They developed trade networks that spanned continents, sharing innovations and resources across vast distances. Within just 10,000 years after the end of the last ice age, humans had spread to every continent except Antarctica, domesticated dozens of plant and animal species, built cities with populations in the tens of thousands, and developed writing systems that allowed them to preserve and transmit knowledge with unprecedented accuracy. This was the final chapter in the story of mammalian recovery from the dinosaur extinction bored people. It had taken 66 million years, but mammals had not only filled the ecological void left by the dinosaurs, they had transcended it entirely. They had produced a species capable of conscious thought, deliberate innovation, and intentional environmental manipulation on a global scale. The asteroid that killed the dinosaurs had ended one evolutionary experiment and begun another. The small furry creatures that survived in the aftermath of that cosmic catastrophe had eventually given rise to something that the dinosaurs, for all their success, had never achieved: intelligence capable of understanding its own origins. We are living in the world that grew from those ashes, bored people. Every mammal you see today, from the smallest mouse to the largest whale, exists because that asteroid happened to strike at exactly the right time, in exactly the right place, with exactly the right force to reset the evolutionary game. The mass extinction that ended the age of reptiles began the age of mammals, and ultimately led to the age of intelligence. And that brings us to the strangest part of this entire story. The catastrophe that seemed like the end of everything was actually the beginning of everything we know. The worst day in Earth's history created the conditions that would eventually produce art, music, science, love, and the capacity to look back through deep time and understand how we got here. The dinosaurs ruled the Earth for 165 million years, but they never developed the ability to contemplate their own existence. They never wondered where they came from or where they were going. They never created beauty for its own sake or asked questions about the nature of reality. Mammals, the small survivors that inherited their world, eventually produced creatures capable of all of these things. We can trace our lineage back through the Pleistocene humans who painted in caves, through the Pliocene apes who learned to walk upright, through the Miocene mammals who developed complex social behaviours, through the Oligocene creatures who specialised in grassland life, through the Eocene giants who experimented with new body plans, through the Paleocene survivors who emerged from their hiding places to find an empty world waiting to be filled. We are the descendants of the meek who inherited the earth, bored people, and we have made something from that inheritance that surpasses anything that came before. We have turned survival into art, adaptation into science, and memory into history. The story of how Earth rebooted after the dinosaur apocalypse is ultimately our story. It's the tale of how destruction became creation, how ending became beginning, how the worst catastrophe in planetary history became the best thing that ever happened to the universe's capacity for self-awareness. Because now, for the first time in 4.5 billion years of Earth's history, the planet has produced creatures capable of understanding their own place in the cosmic story. We can look up at the stars and know we are made of their ancient light. We can dig into the ground and read the history written in stone. We can peer back through deep time and see the thread that connects us to every living thing that ever was. That thread runs through the ashes of the Cretaceous, through the experimental chaos of the Paleocene, through the tropical laboratories of the Eocene, through the grassland innovations of the Oligocene, through the golden age of the Miocene, through the cooling challenges of the Pliocene, through the Ice Age trials of the Pleistocene, and into the modern world where mammals finally learned to question everything, including their own existence. And maybe that's the real message of this story, bored people. Maybe it's not just about how life recovers from catastrophe, but about how catastrophe creates possibilities that never existed before. Maybe destruction and creation are just two faces of the same cosmic process. Maybe every ending is also a beginning, every crisis an opportunity, every apocalypse a chance for something entirely new to emerge from the ashes. The dinosaurs had their moment, and it was magnificent. But their ending made our beginning possible, and our beginning has led to something that transcends anything that came before. The capacity to understand, to create, to love, and to tell stories about where we came from and where we might be going. We are the mammals who inherited the earth from the dinosaurs, and we have made something beautiful from that ancient catastrophe. We are the universe's way of understanding itself, the cosmos made conscious, the final chapter in a recovery story that began with an asteroid and ended with creatures capable of dreaming about the stars. That's the real magic of evolution, bored people. It doesn't just create survival, it creates meaning. It doesn't just adapt to the world, it creates worlds. And sometimes, if we're very lucky, it creates creatures capable of looking back through the entire story and recognizing themselves as part of something larger than they ever imagined possible. So the next time you see a mouse scurrying across your floor or a whale breaching in the ocean, remember that you're looking at a fellow survivor, a distant cousin whose lineage traces back to those dark days after the asteroid hit. We're all part of the same recovery story, all descendants of the creatures who refused to stay extinct, who emerged from the ruins of the Mesozoic world and built something new from the ashes of the old. And that story, the story of how life rebuilds itself after total catastrophe, isn't finished yet. Because we're still here, still creating, still pushing the boundaries of what's possible. We are the mammals who learn to dream, and our dreams have become reality. We are proof that sometimes the best response to apocalypse is not just survival, but transcendence. From ashes to apes to astronauts, bored people. That's how Earth rebooted after the dinosaur apocalypse, and we're still rebooting, still evolving, still writing new chapters in the greatest comeback story ever told. But we're not done yet, bored people, because the story of mammalian triumph has one more twist that'll absolutely blow your mind. While our ancestors were busy figuring out how to be human, something else was happening that would ultimately dwarf even our own success story. We're talking about the rise of the most successful mammalian empire that ever existed, one that's still ruling the planet today, right under our noses. You probably walk past members of this empire every single day without giving them a second thought. They're in your walls, in your basement, in the park where you walk your dog. They've colonised every continent, adapted to every climate, and mastered survival strategies that make human civilization look like a cute amateur experiment. They are the rodents, bored people, and their story is the most underrated chapter in the entire mammalian recovery saga. Now, before you roll your eyes and think, great, we're talking about rats, let me stop you right there. The rodent revolution wasn't just about rats. It was about an entirely new approach to being a mammal that was so successful, so adaptable, so brilliantly simple that it conquered the world without anyone noticing. Picture this. While the Pleistocene megafauna were getting all the attention with their impressive size and dramatic lifestyles, a group of small unassuming mammals was quietly conducting the most successful evolutionary experiment in mammalian history. They weren't trying to be the biggest or the strongest or the most specialised. They were trying to be the smartest about reproduction, adaptation, and resource exploitation. The secret to rodent success wasn't any single trait. It was a combination of innovations that, when put together, created biological machines perfectly designed for planetary domination. First, they cracked the code on reproductive efficiency. While elephants were investing years in raising a single offspring, rodents figured out how to produce dozens of babies in a single year, each one ready to start reproducing within months of birth. But it wasn't just about quantity, it was about flexibility. Rodent reproductive systems could adjust to environmental conditions in ways that would make other mammals jealous. Food abundant, produce more offspring, resources scarce, reduce litter sizes but increase survival rates, predator pressure high, accelerate development and reproduction. They turned breeding into a dynamic response system that could adapt to changing conditions faster than any other mammalian group. Then there were their teeth. Oh, bored people, let me tell you about rodent teeth, because they're basically biological chainsaws that never stop working. Unlike the teeth of other mammals, which wear down over time and eventually limit lifespan, rodent incisors grow continuously throughout their lives. This means they can gnaw through literally anything: wood, bone, concrete, metal cables, without worrying about dental wear limiting their dietary options. This gave rodents access to food sources that other mammals couldn't exploit. They could eat seeds that were too hard for other animals to crack. They could strip bark from trees during winter when other food was scarce. They could even eat their own feces to extract additional nutrients, a strategy so effective that it's called cecotrophy and allows them to get twice the nutritional value from everything they consume. But the real genius of rodent evolution was their approach to body size and metabolism. While other mammals were getting caught up in the arms race toward gigantism, rodents figured out that staying small was actually the ultimate survival strategy. Small size meant low energy requirements, which meant they could survive on food sources that wouldn't sustain larger animals. It meant they could hide in spaces too small for predators to access. It meant they could reproduce quickly and bounce back from population crashes that would devastate larger species. And here's where it gets really impressive. Rodents didn't just stay small, they diversified into every possible ecological niche while maintaining their core advantages. Some became aquatic specialists, like beavers that could engineer entire ecosystems by building dams. Others became arboreal acrobats, like flying squirrels that developed gliding membranes to travel between trees. Still others became desert specialists, like kangaroo rats that could survive without ever drinking water, extracting all their moisture from dry seeds. By the time humans were building their first cities, rodents had already colonized every habitat on Earth except the open ocean. They were thriving in tropical rainforests, Arctic tundra, desert dunes, mountain peaks, and urban environments. They had become the most geographically widespread group of mammals on the planet, and they were just getting started. The real rodent revolution began when they encountered human civilization. While other animals saw human settlements as threats to be avoided, rodents saw them as opportunities to be exploited. Cities provided year-round food sources, protection from weather, and refuge from many natural predators. But more importantly, they provided highways for global expansion. As humans began trading across continents, they inadvertently created a global transportation network for any small mammal clever enough to stow away in cargo holds, grain sacks, and supply wagons. Rodents were the first mammals to achieve truly global distribution, not through their own migration efforts, but by hitchhiking on human trade routes. The brown rat, for example, spread from Asia to every inhabited continent within just a few centuries, travelling in ships and establishing populations faster than any large mammal had ever colonized new territories. These weren't just random introductions. Rodents were actively adapting to human environments, learning to exploit new food sources, avoid new threats, and thrive in artificial ecosystems that had never existed before. But here's what makes the rodent story so fascinating from an evolutionary perspective. They achieved global dominance without developing the complex social structures, advanced cognition, or sophisticated technology that characterized human success. Instead, they perfected a different kind of intelligence, the ability to adapt quickly to changing conditions through behavioral flexibility and rapid evolutionary responses. Rodent populations can evolve resistance to poisons within a few generations. They can learn to avoid traps that have killed their relatives. They can modify their behavior in response to new predators, new food sources, and new environmental challenges. They don't need culture or technology because they have something even more powerful: the ability to evolve solutions to problems faster than the problems can kill them. And their success has been absolutely staggering. Today, rodents make up over 40% of all mammalian species on Earth. There are more than 2,000 different species of rodents, compared to fewer than 400 species of primates. They live on every continent except Antarctica, in virtually every habitat that can support mammalian life. Their combined biomass may exceed that of all other mammals combined, including humans and our livestock. But the most remarkable thing about rodent success is how invisible it's been to most humans. We tend to focus on the charismatic megafauna, the elephants and whales and big cats that capture our imagination. But while we've been watching the dramatic stories of large mammals, rodents have been quietly writing the most successful chapter in the entire post-dinosaur recovery story. They've survived ice ages that killed off mammoths and saber-toothed cats. They've adapted to human-dominated landscapes that have driven countless other species to extinction. They've colonized urban environments so thoroughly that some species are now more abundant in cities than they ever were in natural habitats. They've become so integrated into human ecosystems that our civilizations would probably collapse without them, not because we depend on them directly, but because they've become essential components of the ecological networks that support our food systems. And they're still evolving, still adapting, still finding new ways to exploit the changing world. Urban rodents are developing different behavioral patterns than their rural cousins. Some species are becoming more social, others more solitary, depending on the specific challenges of their environments. They're like living laboratories for rapid evolution, demonstrating how mammalian adaptability can respond to environmental changes within human timescales. This brings us to something really profound about the mammalian recovery from the dinosaur extinction bored people. The story isn't just about the dramatic rise of giants, or the evolution of intelligence, or the development of complex societies. It's also about the quiet perfection of survival strategies that don't make headlines, but that ultimately prove more durable than any of the flashier alternatives. Rodents represent a different kind of evolutionary success, not based on size or intelligence or social complexity, but on efficiency, adaptability, and reproductive strategy. They found a way to be successful that didn't require them to compete directly with larger, stronger, or smarter animals. Instead, they exploited the spaces between, the niches that other mammals overlooked or couldn't access. In a way, rodents embody the essential lesson of the post-dinosaur world, that success in evolution isn't about being the most impressive or the most dominant. It's about finding a sustainable strategy that can survive whatever the planet throws at you. And sometimes that strategy involves staying small, reproducing quickly, and being ready to adapt to whatever comes next. But even the rodent's success story pales in comparison to what was happening in the oceans during this same period. Because while mammals on land were dividing up terrestrial niches, marine mammals were conducting their own evolutionary experiments that would produce some of the most remarkable creatures that have ever lived on our planet. The return of mammals to the sea wasn't just about whales getting bigger or developing echolocation. It was about the evolution of intelligence, social complexity, and cultural sophistication that rivals anything that developed on land. We're talking about animals that developed their own languages, their own traditions, their own forms of art and play that suggest cognitive abilities we're only beginning to understand. The great whales of the modern oceans aren't just large animals. They're floating civilizations with social structures that span ocean basins, communication systems that can transmit information across thousands of miles, and cultural traditions that may be older than human agriculture. They represent the culmination of one of the most audacious evolutionary experiments in mammalian history, the complete reinvention of what it means to be a large, intelligent, social mammal. But to understand how remarkable modern whales really are, we need to step back and look at the bigger picture of how marine mammal evolution unfolded after the dinosaur extinction. Because the story of mammals returning to the sea is actually three separate stories, three different evolutionary experiments that each produced their own unique solutions to the challenges of aquatic life. First, there were the whales and dolphins, which went all in on aquatic adaptation and became so specialised for ocean life that they can't survive on land at all. Then there were the seals, sea lions and walruses, which found a middle ground between terrestrial and aquatic life, maintaining the ability to come ashore while becoming superbly adapted for underwater hunting. And finally, there were the sirenians, manatees and dugongs, which took a completely different approach and became the ocean's gentle giants, specialised for eating underwater plants in shallow coastal waters. Each of these groups independently solved the problems of aquatic life in their own ways, developing different solutions for breathing, locomotion, thermoregulation, and feeding. But more importantly, they each developed their own forms of intelligence and social behaviour adapted to the unique challenges of life in three-dimensional aquatic environments. The story of how these marine mammals evolved from land-dwelling ancestors is so remarkable, so full of unexpected twists and brilliant innovations that it deserves its own chapter in our tale of mammalian recovery. Because what happened in the oceans after the dinosaur extinction wasn't just adaptation. It was the birth of an entirely new form of mammalian consciousness, one adapted to a world without solid ground, without horizons, without any of the visual landmarks that terrestrial intelligence takes for granted. These marine mammals had to reinvent not just their bodies but their minds, developing forms of cognition that could navigate in three dimensions, communicate across vast distances, and maintain social bonds with individuals they might not see for months or years at a time. They created underwater societies that operated by rules we're still trying to understand, using communication systems that are more complex than many human languages. And the most remarkable part, they did all of this while maintaining the essential mammalian characteristics that had made the post-dinosaur recovery possible in the first place. They kept their warm blood, their complex brains, their sophisticated social behaviours, and their ability to care for their young in ways that no fish or marine reptile could match. Stay with me, bored people, because we're about to dive into the deep end of mammalian evolution, where the descendants of tiny, furry land animals became the largest creatures that have ever lived on Earth, and where intelligence evolved in forms so alien to our terrestrial experience that we're still trying to figure out what it means to be conscious in a world made entirely of water. The story of marine mammals isn't just another chapter in the post-dinosaur recovery. It's proof that mammalian innovation was far from finished, that the same evolutionary creativity that had produced giants and specialists and social cooperators on land was about to produce something even more extraordinary in the vast blue spaces that cover most of our planet. Because the ocean, it turns out, was the ultimate laboratory for testing the limits of what it means to be a mammal. And the results of those experiments are swimming around our planet right now, singing songs we can't understand, living lives we can barely imagine, and demonstrating that the mammalian recovery from the dinosaur extinction was even more creative, more successful, and more ongoing than we ever dared to dream. The whales alone represent one of the most successful large animal groups on the planet, with some species more abundant today than they were before human whaling began. They've survived ice ages, climate changes, and even the devastating impact of industrial hunting to emerge as some of the most resilient and adaptable large mammals on Earth. But their story, like all the best stories in evolution, is just beginning. Because mammals are still evolving, still adapting, still finding new ways to exploit the opportunities and challenges of a changing planet. The post-dinosaur recovery isn't a historical event that ended millions of years ago. It's an ongoing process that's still unfolding around us every day. And that brings us to the final, most mind-bending chapter of our story, bored people. Because the mammalian recovery from the dinosaur extinction didn't end with the evolution of humans or the success of rodents or the return to the sea. It's still happening right now in ways that are reshaping our understanding of what it means to be alive on planet Earth. The future, bored people, is where this story gets really weird. Because right now, at this very moment, mammals are conducting their most audacious evolutionary experiment yet, not over millions of years, not through the slow grind of natural selection, but in real time, with conscious intention, using intelligence to direct their own evolution in ways that would have seemed like science fiction to our Pleistocene ancestors. We are living through the next phase of mammalian innovation, and it's happening at speeds that make the post-asteroid recovery look like it was filmed in slow motion. While our ancestors took millions of years to figure out how to walk upright and make fire, we've gone from first flight to landing on the moon in less than 70 years. We've mapped our own genome, learned to edit our DNA, and started the process of extending our reach beyond this single planet. But here's the twist that nobody saw coming. Bored people, the same intelligence that allowed mammals to dominate Earth, is now revealing something that changes everything we thought we knew about our own story. Because the more we study the fossil record, the more we realise that the dinosaur extinction wasn't just the end of one evolutionary experiment and the beginning of another. It was part of a much larger pattern, a planetary rhythm of destruction and renewal that's been playing out for billions of years. Earth, it turns out, is really good at apocalypses. The asteroid that killed the dinosaurs was just the most recent in a series of mass extinctions that have reshaped life on our planet at least 5 times in the past 500 million years. Each one wiped out most existing species and created opportunities for entirely new forms of life to emerge. The mammalian takeover after the Cretaceous extinction wasn't unique. It was just the latest chapter in a story that goes back to the very beginning of complex life. And that realization has led to something that our Paleocene ancestors, hiding in their burrows, while the world burned around them, could never have imagined. We've become the first species in Earth's history that's aware of this pattern, that can see the bigger picture of planetary evolution and our place within it. We're not just another successful mammalian species anymore. We're the first form of life that can consciously participate in the process of evolutionary change. Think about what that means, bored people. For 66 million years, mammalian evolution was driven by environmental pressures, climate changes, and random events beyond any species' control. But now, for the first time in the history of life on Earth, one species has developed the ability to consciously direct evolutionary processes. We can preserve species that would otherwise go extinct. We can bring back species that have already disappeared. We can even create entirely new forms of life that never existed before. We're conducting experiments in directed evolution that dwarf anything that happened during the natural recovery from the asteroid impact. We've domesticated dozens of species so thoroughly that they're essentially living sculptures shaped by human intention rather than natural selection. We've created global transportation networks that allow species to colonize new continents faster than they could during any previous geological epoch. We've altered atmospheric chemistry, ocean acidity, and global climate patterns in ways that are creating entirely new, selective pressures for every living thing on the planet. But the most remarkable thing we've done is something that no previous species ever achieved. We've developed the ability to look back through deep time and understand our own evolutionary history. We can read the story written in rocks and bones and DNA. We can trace our lineage back through the entire mammalian recovery, through the age of reptiles, through the earliest emergence of life itself. We've become the universe's way of understanding its own history, and that understanding has revealed something profound about the nature of extinction and recovery, because the more we study mass extinctions, the more we realise that they're not just random catastrophes, they're opportunities, they're reset buttons that allow evolution to explore possibilities that would never emerge in stable ecosystems. The asteroid that killed the dinosaurs didn't just end the Mesozoic era, it created the conditions that made everything we value about life on Earth possible. Without that cosmic catastrophe, mammals would probably still be tiny, nocturnal creatures scurrying through the underbrush of a dinosaur-dominated world. There would be no whales singing in the oceans, no elephants trumpeting on savannas, no primates swinging through forests, and certainly no humans contemplating their place in the cosmos. The worst day in Earth's history was also the luckiest day in mammalian history. But here's where the story takes its final, most incredible turn: bored people. Because we're not just studying this pattern of extinction and recovery, we're preparing to transcend it. For the first time in the 4.5 billion year history of our planet, one species has developed the technology and knowledge necessary to survive any catastrophe, even ones that would make the asteroid impact look like a minor inconvenience. We're developing the ability to live in space, to establish self-sustaining colonies on other worlds, to preserve the entire genetic heritage of Earth in digital formats that could survive planetary destruction. We're becoming the first species that could potentially survive the death of our own planet, carrying the story of mammalian evolution to other worlds around other stars. The mammals that inherited the Earth from the dinosaurs have produced something that transcends biology entirely: the ability to preserve and transmit information across cosmic distances and geological timescales. We've become evolution's way of backing itself up, ensuring that the story of life on Earth could continue, even if Earth itself were destroyed. And that brings us to the most mind-bending realization of all. The mammalian recovery from the dinosaur extinction wasn't just about filling empty ecological niches, or getting bigger, or developing intelligence. It was about creating the conditions for consciousness to emerge, for the universe to become aware of itself, for information to become more important than biology. We are the end result of 66 million years of mammalian evolution, bored people, but we're also the beginning of something entirely new. We're the first form of life that can consciously direct its own evolution, that can survive any catastrophe, that can spread to other worlds and carry the story of our origins with us. We're not just mammals anymore, we're something unprecedented in the history of the universe. The story that began with a mountain-sized rock screaming out of space has culminated in creatures capable of travelling to space themselves. The lineage that started with tiny furry animals hiding from the firestorm has produced beings capable of preventing future firestorms or surviving them if they can't be stopped. The evolutionary experiment that began in the ashes of the Cretaceous has created the first species capable of ensuring that no asteroid, no climate change, no mass extinction will ever again wipe out the accumulated knowledge and creativity of 4 billion years of evolution. That's the real miracle of the mammalian recovery, bored people. It didn't just produce successful species or complex ecosystems or even intelligence. It produced hope. It proved that life doesn't just survive catastrophe. It uses catastrophe as an opportunity to become something better than it was before. Every mammal alive today, from the tiniest mouse to the largest whale to the humans reading these words, exists because 66 million years ago, a cosmic accident gave evolution a chance to start over. And evolution didn't just restore what was lost, it created something entirely new, something more creative and adaptable, and ultimately more hopeful than anything that had come before. We are the proof that destruction is not the opposite of creation, but its partner. We are the evidence that endings are also beginnings, that every catastrophe carries within it the seeds of something unprecedented and beautiful. We are the mammals who inherited the earth from the dinosaurs, and we have made something from that inheritance that surpasses anything that came before, or anything we can yet imagine. The asteroid that ended the age of reptiles began the age of mammals, and the age of mammals has given birth to the age of consciousness. And consciousness, it turns out, is just getting started. We are still evolving, still adapting, still writing new chapters in the greatest comeback story ever told, from ashes to apes to astronauts, to whatever comes next, bored people. That's how Earth rebooted after the dinosaur apocalypse, and the reboot is still running, still processing, still computing new possibilities from the infinite potential that was released when that ancient mountain fell from the sky and changed everything. The story of mammalian recovery is also the story of cosmic awakening, of matter becoming complex enough to contemplate its own existence. And that story, the story of how the universe learned to think, is still being written by every mammal that dreams, every whale that sings, every human that wonders, and every possibility we haven't even imagined yet. Because in the end, bored people, that's what the mammalian recovery really achieved. It didn't just fill empty niches or develop new body plans or even create intelligence, it created wonder. It produced creatures capable of looking back through deep time and being amazed by their own existence, creatures capable of feeling grateful for cosmic catastrophes, creatures capable of finding beauty in the story of how everything died and everything began again. And that wonder, bored people, is still spreading. Right now, at this very moment, somewhere in your city, a brown rat is solving a puzzle that would stump most other mammals. Somewhere in the Pacific, a blue whale is singing a song that carries information across ocean basins in patterns we're only beginning to decode. Somewhere in a forest, an elephant is teaching her daughter to remember the location of a waterhole that saved their family's lives 30 years ago. The mammalian revolution isn't over. It's accelerating, and the most incredible part is that we're finally smart enough to watch it happen in real time. But here's what keeps me up at night. Bored people. Here's the thought that makes this whole story feel less like ancient history and more like a preview of coming attractions. Because we're not just studying the mammalian recovery, from the dinosaur extinction anymore. We're living through our own version of it. Right now, in the span of a single human lifetime, we're witnessing environmental changes that rival anything our planet has experienced since that asteroid hit. Climate is shifting faster than it has in millions of years. Species are going extinct at rates that approach mass extinction levels. Ocean chemistry is changing. Ice caps are melting. And in the middle of it all, mammals are adapting in ways that would make their Paleocene ancestors proud. Urban mammals are evolving different digestive systems to process human food waste. Arctic mammals are shifting their migration patterns as ice disappears. Marine mammals are changing their communication frequencies to cut through the noise of ship engines. Some species are going extinct, yes, but others are thriving in ways that would have been impossible in the pre-human world. We're not witnessing the end of the mammalian story, bored people. We're witnessing its next chapter. And this time, instead of being written by asteroids and ice ages and random climate shifts, it's being written by conscious intention. By the one mammalian species that learned to think about thinking, to plan beyond its own lifetime, to care about the survival of other species not because they're useful, but because their stories matter. That's the real plot twist in the tale of mammalian recovery. It didn't end with humans becoming the dominant species on Earth. It ended with humans becoming the first species capable of ensuring that dominance doesn't lead to extinction. We've become evolution's insurance policy, the backup drive for the entire experiment of complex life. And maybe that's the most hopeful thing about this whole incredible story. The mammals that survived the dinosaur extinction by being small, adaptable, and cooperative eventually produced a species capable of making sure no future extinction ever has to start from scratch again. We've become the keepers of the flame that was first lit in those dark days after the asteroid hit, when tiny, frightened creatures emerged from their hiding places and decided to build something new from the ashes of the old. Every time you see a squirrel in your backyard, remember that you're looking at a direct descendant of the survivors who rebuilt the world after its worst day. Every time you hear about a new species being discovered or an old species being brought back from the brink of extinction, remember that you're witnessing the continuation of a recovery story that began 66 million years ago and is still unfolding. The dinosaurs had their time, and it was magnificent. But their time ended so that our time could begin. And our time, the age of conscious mammals, of creatures capable of love and art and science and wonder, is still just getting started. So here's to the mammals, bored people. Here's to the rodents in your walls, and the whales in your oceans, and the primates reading these words. Here's to the survivors who inherited a broken world and fixed it not just once, but over and over again, for 66 million years and counting. Here's to the proof that catastrophe is not the end of the story, it's just the beginning of a better one. From ashes to apes to whatever comes next, the mammalian recovery continues, and we're all part of it, whether we realise it or not. The greatest comeback story in the history of life on Earth is still being written, one heartbeat at a time, one breath at a time, one moment of wonder at a time. And that, bored people, is how Earth rebooted after the dinosaur apocalypse. Not with a bang, but with a whisper. Not with conquest, but with cooperation. Not with an ending, but with the endless beginning of everything that makes life worth living. The asteroid is still falling in a sense. Change is still coming. Challenges are still ahead. But we're mammals, damn it. We're the descendants of the creatures who looked at the worst day in planetary history and said, challenge accepted. And we're still accepting challenges, still adapting, still evolving, still proving that the best response to apocalypse isn't despair. It's creativity. It's the audacious belief that whatever comes next, we'll figure out how to make something beautiful from it, because that's what mammals do. We take the ashes and build worlds. We take the silence and fill it with song. We take the darkness and kindle fire. and 66 million years later, we're still burning bright. Thanks for staying curious, bored people. Thanks for taking this journey through deep time with me. And remember, you're not just watching this story unfold, you're part of it. You're living proof that sometimes the best things in the universe come from the worst things that ever happened. Sweet dreams, mammals. The future is still being written, and you're holding the pen.